What we have done yesterday, hopefully we have understood the basic equation of a traveling wave. And this is the wave equation. And this is equation of a transverse wave, which means a wave is traveling along x direction and every particle on the string is oscillating along y-axis. And what does, see, let's try and again look at this, understand this equation. What factor the omega depends on? Omega depends on angular frequency of a source which is causing oscillation. What does x indicate? X indicates position, a particular particle on the string. X indicates particular particle on the string for different, or it gives a position of particular particle on the string. And for any given x, the particle moves, nature of motion of particle is along y-axis. So any particle which is there on the string, this x coordinate does not change. That's the transverse wave. A is amplitude. And in case of a string, whatever amplitude of oscillation we have at source, since amplitude oscillation, all points undergo. And what we notice here, if you look at this wave equation, there are two variables here. One is a x variable, other is a t variable. So we can find a rate of change, we can differentiate with reference to time, which we have done yesterday. If we differentiate this equation with respect to time, which is dy by dt, and dy by dt gives me velocity in y direction, which is particle velocity in y direction. So when we differentiate with reference to time, we can obtain an expression for velocity in y direction, transverse direction. What happens if we differentiate with respect to x? So let's see, what does dy by dx indicate? And dy by dx, I think most of you will be familiar with. Dy by dx is expression rate at which y changes with x, which is nothing but slope. So any curve which is there, for any curve, dy by dx indicate slope of the tangent drawn at a particular point. So if I differentiate dy by dx and substitute a particular value of x and particular value of t, it will indicate slope of a tangent drawn to the curve at an instance t naught at a position x naught. So this indicates slope to the tangent. So when a particular, suppose this point is this particular shape of the curve, or shape of the string is at time t naught. This is the shape of the string, or you can also call this is the shape of a wave at particular instance of time. And there's a particular point P here, and this is at this coordinate is x naught. So if I dy by dx, if I substitute these values, it will indicate slope of the tangent drawn at this particular point at this particular instance. So that is dy by dx indicates slope at a particular point at a particular instance. And let's understand what is the significance of slope. So if let's say it's this equation, let's obtain what is dy by dx. So if I differentiate again, and if I differentiate reference to x here, coefficient is minus k. So minus k comes in here. It becomes this is expression what we obtain, very simple derivative with reference to x. This expression, and we already know what is dy by dt. Dy by dt in that case, again the coefficient of t comes here, which is omega here, and this term, this expression. What you notice here, both cases, this term is common. Both cases we are getting a cos expression and a also. So what you notice here, this seems to be, this is slope and particle velocity seem to be related. And from here, this is particle velocity. So this particle velocity I can write in terms of slope. If I substitute value of a cos omega t from previous equation, it becomes particle velocity becomes minus omega by k into slope. And what is omega by k? Omega by k is nothing but speed of the wave. Okay. So what is particle velocity equal to? Minus v times slope. So particle velocity is, and in terms of, let's look at in terms of dimensions also. Slope is a dimensionless term. This is wave velocity. So particle velocity is negative of wave velocity multiplied by the slope. That's the expression of particle velocity. And let's try and understand how it makes sense. So, if can v be positive or negative? Wave velocity. In this particular case, wave is traveling towards right direction. Wave velocity, if it is positive, So when wave is traveling along positive x direction, v is positive. It means wherever v is positive, wherever slope is negative, particle velocity is positive. And when slope is negative, sorry, negative slope, particle velocity is positive, and positive slope, particle velocity is negative. Let's try and understand from this figure also. So let's look at this here. Which part, this is the shape of the wave at particular instance of time. And where is, which part is the slope positive here? When I look from here, this point, the slope is 0. And this point slope is 0 at this particular instance. So between V to B to E, the slope is positive. And velocity of it, the slope is positive and velocity also is positive. So particle velocity should be negative. It means all particles between B and E are having at this instance negative velocity. What is, and you can understand from the dotted line also. So how this particle has moved, this particular in next small time interval, it has shifted from here to here. This particle has moved from here to here. Or if we draw, this is how all particle has moved. What do you understand from here? Based on the slope also, for positive velocity, slope is positive, velocity, particle velocity is negative. And if you look at this part of the curve, here slope is negative and particle velocity should be positive. That's how the particle velocity will be. So this is very simple relationship and nothing too special, but we can understand how there are two variables here. We can differentiate with reference to time, we get particle velocity. We differentiate with respect to x, we get the slope. And those two terms are related. And one velocity is in terms of, it is related to other velocity with the some constant. Slope is a constant. So wherever slope is more, so what, let's one understand one more thing here. So among all the particles between B to E, based on this equation, which particle will have maximum velocity? There's all particles on the string which are between point B and E, all of them have negative velocity at this instance. They are moving downwards. But when they move downwards, which one will have maximum particle velocity? So when I look at this, particle velocity will be maximum, where slope is maximum, because wave velocity is fixed. So which point is the slope maximum here? We understand from here, any sine curve, slope is maximum. Yeah, derivative of slope per sine curve, sine is what? Cos. So cos function is maximum for theta is equal to 0. So here also, which point is the slope maximum? This is the point where slope is maximum, and this is the point where slope is 0. So particle velocity is 0 here, is 0 here. From here, particle velocity progressively decrease, and this is the point where particle velocity is maximum, which we know in terms of property of SHM equation also. Okay, so this is our understanding of two derivatives of equation of a wave. So what we understand here, for positive wave velocity, particle velocity up when the slope is negative. What if we take the second derivative? We have done that for a second derivative with reference to time yesterday. The second derivative of, with reference to time, this expression. Okay, and this is nothing but acceleration. And similar way, if we take the second derivative with reference to x also. So again, we differentiate again this part again. And what is the expression we obtain? We differentiate this part again. If we differentiate this part again, this expression we obtain here. So again, we find the acceleration is related to second derivative with reference to x. And how do we interpret x here? dy by dx is slope. What is dou square y by dx square? What does this term indicate? Can we define this term here? How do we define this term? dy by dx we define as slope. D square y by dt square we define as acceleration. What is this equal to? This term is nothing but the d by dx of slope, which is rate of change of slope. How the slope is changing, at what rate is the slope changing. And from here also, if we take the ratio, if we divide this equation by this equation, on the right hand side we'll get omega square by k square. And omega by k is nothing but particle. Omega by k is what? Omega by k is, what is omega by k term? Is a wave velocity. The ratio of these two is equal to square of wave velocity. And wave velocity is constant. If we write this equation and ratio, and then we take the denominator to the other side. So this expression is, and other way to interpret this equation is, and this becomes one additional condition for wave equation. the second derivative with reference to time and second derivative with reference to x, their ratio is constant. Then only it's a wave condition. And what is the ratio equal to? Ratio is equal to square of wave speed. And that's how I was mentioning yesterday. There's one more condition for wave motion or wave equation. So any wave equation must satisfy this condition as well. Okay. And so far we talked about wave velocity. Let's say understand this equation, this figure here. This is a string here. The blue color string is shown here, and it is under tension. So the string is held horizontal. For a moment, ignore gravity. So string, if it does no, ignore the effect of gravity, tension is enough, and let's say it is gravity-free space. So if we apply horizontal force, which is at the same level as the support, the string also is horizontal. And how do we create oscillation? To create oscillation, we need to move this point. Suppose if we were to move this point up, what we need to do? To move this point up, this tension also need to become inclined. So when this tension force becomes inclined, it moves this particle in the upward direction or downward direction, depending on which direction we incline. And as we incline the force, what will happen? This particle will start moving up. And since all have linked to each other, if this particle moves up, it tries to drag the next one, next one, next one, and it makes all adjoining particles move up with some time lag. That's what happens in case and this disturbance which is created here, it travels along the string at a certain speed, certain wave velocity. Let's see, can we derive this wave velocity? So this is something we'll use laws of motion to derive this wave velocity. And you'll notice this derivation I'm doing a slightly different way compared to what is given in most of the books, because this I feel is more intuitive. So let's arrive at wave velocity from laws of motion. The string is under tension and it will depend on mass. So, if the mass is more, it will be more sluggish in response. Mu is the mass per unit length of this string. Let's see how do we arrive at wave velocity based on certain assumption. Yes, of course, the wave velocity, somebody must have derived it. Somebody must have thought of some way to find wave speed on a string. So let's assume that end of the string is moved up with the constant velocity Vp, particle velocity. We are given a constant velocity in vertical direction Vp by applying a force T inclined at angle theta. So rather than making the force horizontal, we have made the force inclined. And because of inclined force, this particle is moving at velocity Vp, and we are taking very small element. It is exaggerated. We are taking very small element of string here, so that even if this becomes curved, it can be taken as straight. Very small element, so we can take as a straight line. So what has happened when he applied this force here? This particle start moving, and all this particle also. See, if it retains a straight line shape, it can retain a straight line shape only when all particles have same velocity Vp. So when we apply force, after some time, I find this is the part of the string up to which the wave has traveled or disturbance has traveled, and let this distance be x. So how much part of the string where wave motion has traveled? Distance x. And because this effect of this motion here, all these particles in the string have acquired a velocity Vp in the vertical upward direction, and this part of the string is still unaffected. But as the time goes, more and more part of the string will get affected. And that's what we need to find at what is the rate at which the disturbance will travel or wave will travel on the string. Let's see that. So with time, more and more length of the string particle will acquire velocity Vp. So this is something what will happen after some time. You see, up right now it is only up to travel up to this point only. After some time it will travel further up. Let's understand. Let's take the up to, it has traveled up to distance x in time t. If we take some extra time for further time, this x also will increase. Let's say time t plus delta t. What is this time here? From t to delta t. In additional time of delta t here, it has traveled additional distance delta x. Okay. So let the distance be, so how much distance extra? This is in time, extra time delta t. It has traveled additional distance up to this point, the wave has traveled. Now, can we form an equation based on laws of motion between this instance and this instance? What has happened here? Now, earlier only this particular mass was having a velocity Vp in the vertical direction. Now this much mass is having velocity in vertical direction. What does it mean? In time delta t, this is the additional part of the string, or this is the additional mass which has acquired a momentum in the y direction. Okay, so there's a change in momentum, and there's a reason why there's a change in momentum, because there's an impulse acting here. So if I consider this as my system, earlier this was a part of my system, now this has become my system. So what has happened, if I take this part here, this much part which has no momentum earlier, this also has acquired momentum, and this part has remained same. So can we, from this instance and this instance, can we calculate impulse which has been applied in y direction and change in momentum? What is the impulse applied in y direction here? Time interval is delta t. Can we calculate impulse here? Can anyone tell me what is the impulse in y direction? What is impulse in y direction? So force in y direction into time interval. And what is the force in y direction? T sine theta, which is nothing but f into theta, small angle. This is all very small angle, and into delta t. This is the impulse we have applied in y direction. Can anyone tell what is the change in momentum here? Change in momentum is a momentum acquired by this part. What is the momentum this part has acquired? Mass into velocity. So change in momentum will be equal to take delta py. How much will be the change in momentum be equal to? Mass m into Vp. That's the change in momentum. Earlier momentum was zero, this momentum it is required. So we can equate the impulse with change in momentum. Let's write this equation. In y direction, impulse is equal to change in momentum. So t sine theta, which is equal to t theta delta t, equal to delta m into Vp. Okay, and this is velocity with which it is being moved up. Now, what is delta m here? Delta m is nothing but mu into delta x. This distance is dx, delta x. So this expression we get here. We substituted all these values. Slope is nothing but delta y by delta x. That's the slope equation. Now, do we identify the velocity, wave velocity term here? Where is the wave velocity term here? What is wave velocity? Wave velocity is, it has moved by distance delta x in time delta t. Delta x by delta t is my wave velocity. So can I find this term here? These two terms will cancel out. So if I take t by mu is equal to square of delta x by delta t square. So basically t by mu is equal to v square, or v is equal to root of t by mu. So even if you don't understand the equation, this derivation has, I think this derivation is not too important. You just understand the basics of the derivation. So what is wave velocity? Wave velocity in a string is equal to root of t by mu. Yes.
Sir, I understand why you took the theta as delta y by delta x. I mean, the same delta y by delta x.
Okay. Any straight line, but basically, I thought this is a very standard definition. For what is slope for anything? Any straight line, what is slope?
So we're assuming it's in the same line, sir?
Yeah, we are assuming it to see, we are taking very small element. So any small element we can assume to be straight. Okay. And this expression. So this is something, see, what would have happened? Somebody would have thought of some way of calculating this wave speed, and using laws of motion, this how they would have calculated. And then again, they verify it matches with the actual speed what we observe, and it does match. And there are other ways also. There are a couple of other ways of also of calculating wave speed. In all cases, we get a similar expression. And in your syllabus NCERT book, they have calculated wave speed using dimension analysis. Simply dimensions. Wave speed is a function of tension as well as mu. And we're using dimensions. How do we, what exponent t and mu should have so that dimensions match, and we get this expression. But this gives some idea about how the wave travels and what the wave speed is. It will depend on t by mu. And that's the expression. It's an easy formula to remember, and it's an important formula for this chapter. So what is speed? Root of t by mu, t being the tension in the string, and mu being the mass per unit length. That's the speed which wave will travel. So what will happen? So wave speed for a given string for a given tension, speed wave is same. what we can happen, we can have different value of omega. As the value of omega changes, what will happen? The wavelength will change. For different omega, we'll have different wavelength. But so as omega, if wave speed is only a function of, so wave speed does not depend on frequency of oscillation here. As we change the frequency of oscillation, the wavelength will change. So wavelength is a self-adjusting length. Okay, so let's understand rate of change of slope. What is rate of change of slope? They have slope term theta, d by dx or rate of change of slope. So let's understand from here. See, suppose from here, if I look for point this between these 2 points, what is happening to the slope? Slope is gradually decreasing from here. This point in sine function, this is the point where slope is maximum. And here the slope becomes zero. Slope is zero. And what is happening in between? The slope is continuously changing. Let's try and understand. And this also, I would say, is an optional topic. If you understand is good, but this derivation is not too important. So but even no harm in trying to understand what does it mean. So what is, if I take this derivative, rate at which the slope changes, let's see what does it mean. So let's take a small part of the string here. Again, similar to the previous case, we take a small part of the string between which coordinate, between x position x and x plus delta x. So length of that string will be delta x, and two ends, it will have, one end will have a different slope and other end will have a different slope. And everywhere what is happening, the tension T is acting tangentially. Okay, so let's look at this. And what are we going to do here? We'll take this small element of the string here, and we are going to apply laws of motion here as well. And let's see what is result we get here. Okay, so let's take a small piece of string. So I have just magnified. So this end of the string, what is the coordinate here? Position of left hand of the string is x, and length of the small this is delta x, and it has certain slope here, theta, and this is theta plus delta theta. Of course, delta theta is negative, but just for understanding, what is the slope here? This slope is theta plus delta theta, and this slope here is theta. So when we take this part of the string as a system, what are the forces acting on this part of the string? This part is connected to string on other side and other side. So when we take a small part here, I have to apply contact force, which is tension force here and tension force here. Which direction the tension force will act? Tangential force acts in the tangential direction. So a T is acting like this here, and a T is acting like this here. So this is the object. This is the free body diagram. Of course, I can represent as a point. So this is the force which is acting. And had the slopes been equal, these forces would have cancelled out. They would have been equal and opposite. But since the slopes are not equal, they give rise to a net force in the vertical direction. We'll ignore horizontal component here. Net force, it will give to net force in the vertical direction. And since there is a net force in the vertical direction, this piece of string will get accelerated. So some of you can understand this point here. What is causing acceleration of the string in vertical direction, a piece of a string in the vertical direction, is a difference in slope between two ends. Since the slopes are different, the tension force is acting at different angles, hence it will have different vertical components, and hence it will have acceleration. Let's write these expressions now. Applying laws of motion. What is force acting? So for which direction? Y direction. So here, since all angles are small, displacement is small. It is all exaggerated. Otherwise, you can think of motion of a wave on a string or something similar to what you see a vibration of a guitar string. The guitar string also, there it vibrates, but amplitude of vibration is extremely small, hence the slopes are also small. So the slopes are small. So this is vertical component, T into sine theta, and sine theta can be extended as theta. So this is net force acting, and net force has to be equal to mass into acceleration in y direction. Mass is mu times delta x length, right? So what is this? This we are left with T into delta theta and mu into delta x. And what is ay? Ay is equal to d square by dt square. So if this length delta x is small, I bring this delta x here. So this becomes denominator delta x, it becomes t into d theta by dx, very small value. So again, I'm assuming delta x is tending to 0. So this expression, this term is brought here. So this is the expression we get here. And what is theta? Theta is nothing but dy by dx. So what we get here is, we get t by mu to this side. T by mu is equal to d square by dx square is equal to this expression, which is same expression as what we have seen earlier. This is a similar expression. Okay, and this is the condition. So where from we got this expression? There, previous case we already had a wave equation, and this condition we have not assumed this shape of the string to be sine function. It is valid for any shape of a wave. We have arrived this condition based on laws of motion. So this condition must be valid for any feasible wave shape. What is this? Rate of change of slope. And what is t by mu? And this t by mu is nothing. We know already t by mu is t by root of t by mu is velocity. And so t by mu is square of wave velocity. Okay. So ratio of second derivative refers to n, x, and t and x are constant. So, what is the important part, or which part has a lot of applications of what we have done so far? The part which has a lot of application is this. Velocity of wave on a string is equal to root of t by mu. And let's understand here, and one common arrangement. There are a number of ways we can have a wave set up on a string. One wave is something similar to guitar or any musical instrument. And we use something called, this kind of setup we call as a sonometer. So what happened, there's a kind of peg. We can see in the guitar also there's a kind of peg here. So we make a pointed support here. It's like a small bridge kind of thing. We call it a bridge here. And the wire is run over the bridge. And there's a smooth pull, there's ideal pulley. And depending on what is the mass we suspend here, the tension can be varied. And by changing the position of the bridge, the length of the wire can be varied. Only thing, for if we choose a particular string like a guitar string, it will have particular mass per unit length depending on which material and what is the radius of the wire. So this is a kind of setup. If we suspend mass m here, it creates certain tension. And this kind of setup, we can change this tension here, we can change the length of the wire, and we can use a different wire also. And this kind of setup we can use for setting up a wave in a string. And this is called a sonometer. So this equation, let's try and understand what is mu here and how do we obtain mu. Mu is mass per unit length. And mass per unit length is also equal to density into area. If I take unit length of area, so length is equal to, L is equal to 1 unit, and area of cross section is A. Hence volume will be equal to A, and volume is equal to A. The mass will be equal to density into volume, hence equal to rho into A. So mass rho, mu is equal to rho into A, area of cross section, and the circular cross section rho into pi r square. So any of these terms might be given. It can also be written in terms of density. It can also be written in terms of radius also. That's a mu term. And this kind of arrangement is called a sonometer. And sonometer, what is the tension in the string here? So tension in the string is equal to weight which is suspended here. And this you may have some questions. So weight can be changed. We can make weight 4 times. And what will happen? There are also some questions where whatever weight is suspended, suppose we immerse in some liquid. If you immerse into liquid, what will happen? The weight will become like what you call as apparent weight. It will become weight minus force of buoyancy. So what will happen? Tension will change. So whenever weight is immersed, it will be weight minus Fb. That will become my tension. Otherwise, what is tension? Tension is nothing but equal to weight of the mass which is suspended here. Okay. So other case is something. So what happens? This another case could be something like this. So suppose we take a rope kind of thing. If we suspend a rope vertically, and we know from laws of motion, if we suspend the rope vertically, and this rope has some mass m and length is L. So what happened? It has mass per unit length is equal to m by L. And if we take different parts of the rope at different heights, what will happen? Tension will keep on changing. What is the tension at a particular point? Tension at any particular point will be equal to, we can find the tension by taking the part of the rope below that point of suspension as free body. If we take that as a system, so if the length is x, so tension will be equal to weight of the rope below a particular point. What is tension at a particular point is equal to weight of the rope below that particular point. So as the weight will keep changing, tension also will keep on changing. So we'll have a variable tension kind of questions also. So I'm just looking at this a question. We can have this kind of applications and different types of questions based on wave velocity. Let's go through. So this is so only thing new what we have done today is we have taken derivative with reference to x. We understood the slope of a waveform, and we also understood rate of change of slope. As the slope changes, rate of change of slope, as the slope changes, difference in slope only gives rise to net force in y direction, gives rise to acceleration. And second thing, we have derived one formula, which is t is equal to, wave velocity is equal to root of t by mu. Let's go through some applications of the same equation. What is hanging mass? So this equation given, what we need to do, just all of you just read through the equation, pretty simple question. What are things we know? Density is given, area of cross section is given, hanging mass has to be formed. If mass is m, what we understand here, the tension in the string is equal to mg. That we understood. And if this equation given, wave velocity is given. So what are things we know? First thing we understood, tension is equal to mg. Second thing, from wave equation, we understand wave velocity. What is wave velocity? Wave velocity is omega by k, which is also given. And area of cross section string is A and density is rho. So basically mu value also is given. Mu is equal to rho into area. And since we have to find hanging mass, we use the condition wave speed is equal to, we relate this quantity using v is equal to root 2 by mu and easily get an expression. So fairly simple question. I hope all of you understood. We just substitute to get your answer. Next question. Okay, this again transverse wave propagating on a string with the linear density mu value is given, which is given in SI unit. When we are solving a question, we have to make sure if we are solving an SI unit, everything has to be in SI unit. This is how it is represented, where x is in meters and t is in second. So when we take derivative, we'll get the wave velocity in meter per second. We have to, what is the tension in the string, we have to calculate. So this also a fairly simple question. We have to calculate tension in the string. And this also based on wave speed, v is equal to root of t by mu. And mu term is directly given. Wave speed is given, we will differentiate, we find the wave speed. Actually, in this case, is traveling in negative x direction. And wave velocity is equal to what? 60 by wave velocity is equal to 60 by 1.5. So with this also simple substitution, we get t value. This value is given. From this equation, we get value of wave velocity. Mu is directly given, we can find t here. Let's understand this question here. And those who play guitar and all also can understand a little better. So let's say this is something, so okay. So suppose we have a wire of length L. It is placed between two fixed supports at a distance L apart, and initially it is just taut. Means it is not hang, it is not loose, it is just tight, but at this instant tension is just taut, means tension is negligible. So this length is L. Now, suppose what happens if I move this support here by distance delta L or delta X. If I move, I'm basically when I move this one of this fixed support, I'm stretching the wire. The wire length, it gets stretched by length delta X. When it gets stretched by length delta X, we know from equation Young's modulus. What is Young's modulus equation? Force is equal to, what is delta X? Delta X is equal to flare F into L by AY. And so here, so moment we stretch the wire, a tension force will develop, which is equal to F. So what force develops? We can understand the force in two ways. I can write the force as equal to, what is F equal to delta X by L into AY. And this term is nothing but strain, and this is Y. So the strain into, this term is strain. The force is equal to strain into Y into area. Sorry, strain into Y into area. What is strain into Y, which is called stress into area. So when, and more we stretch, So rather than having delta x, suppose we extend by 2 delta x, what will happen? Tension will become double. So what we understand from here, wire also, I think I mentioned earlier, wire also behaves like a spring. So tension force which develops is proportional to its elongation. So this question is based on this. Extension of the wire obeying Hooke's law is x. And when extension is x, there's some tension T. So corresponding to initial case, okay, and T is equal to some k times x. Extension is x, is proportional to x, that's what you can say. And at this time, velocity speed is v. And v will be equal to what? It is equal to T by mu. That's initial case. What will happen if the extension of the string is increased to 1.5x? We could have solved very quickly. When we increase the extension of the spring, when next case, final case, what happens? T dash is equal to k into 1.5x, which is equal to 1.5 times t. So when the tension becomes 1.5 times t, velocity also will become root of 1.5 times. So what will v dash be equal to? V dash will be equal to root of 1.5 into v. And roughly what is root of 1.5? See, 1.44 square root is 1.2. So it will little more than 1.2. So this will be little equivalent to 1.2 V plus something. So which is the option which is closest 1.2? This is the option. So these questions also, yes.
So why are we getting speed of sound here, sir? How is it related? Like this is not wave speed we are calculating, right? V
See,
here is
actually, the word sound has come, will come to wave speed. Even if you vibrate also, it will be same. And can the sound also travel? Actually, sound also creates vibration. Can the sound also travel through solids? Do you think the sound can travel through solid?
yes, sir.
Has anyone tried that one? But this is some people use that one kind of plastic board. You connect by a rope, and two people. You make a small kind of plastic cup. You can hold two plastic cups. You connect a plastic cup by wire. If two people stand here, one person here, and this may be significant distance, maybe some large distance like 20 meters. When this person directly speaks, you hear certain sound. But this person, if you speak in this cup here and other person keeps your ear near the cup, you find the sound is much louder. How is the sound traveling in that case? Sound is traveling through the string here. So sound can travel through that medium. We'll come to that part also later. But yes, sound can travel in any medium. In a string also, sound also can travel. But when the sound travel, it's a longitudinal oscillation, but basic principle remains same. So that's the same principle you're using it here. We'll come to the sound also later, but sound also is a wave. The way oscillating wave travels like this, a similar way sound wave also can travel. It follows the same equation, same principles. Let's look at the next question. There's a uniform rope of length 12 meter. So let's say this is the rope here. The length of the rope is 12 meter. And mass is equal to 6 kg mass, which basically means what is mu equal to? Mu is equal to 0.5 kg per meter. Hangs vertically from a rigid support. A block of 2 kg is attached to the free end of the rope. So here also we add a block of 2 kg at free end of the rope. We generate a pulse. Here we create oscillation. We generate pulse means something like this. We created a pulse, something like this. So when we create a pulse here at the bottom, it has certain wavelength here, lambda naught. And this way, here we create a pulse, it will travel. And what it says here, so when we wavelength here is, we create a wavelength here is equal to 0.06 meter at the lower end of the rope. What is the wavelength of the pulse when it reaches the top of the rope? So when it reaches this here, what is the wavelength here? Why would the wavelength change here from here to here? First of all, can you think why should the wavelength change? First question. Why basis, why and what, how we can calculate? Why should the wavelength change? Anish, can you think of a way? Why should the wavelength change? Anish,
Yes, sir.
can you think of a reason why should wavelength change?
Maybe it's non-uniform.
So we have to think of what factor does the wavelength depend on. So basically V is equal to, what is velocity of wave? Velocity of wave is, we can think of one equation, V is equal to F lambda. So velocity in a string is equal to frequency times lambda. So is the frequency here and frequency here? Will the frequency be different or frequency be same? Frequency depends on the source. As the wave is traveling, the frequency here and frequency remains same. The frequency depends on the source, frequency is not changing. But what we notice here, velocity is changing. Why is the velocity different? So why wavelength change? Because reason for wavelength change is velocity of the wave is equal to F lambda. And F frequency remains constant. The frequency remains constant. It depends on the source. Whatever frequency oscillation we have created, same frequency will reach here. Depends only on source. So what does this mean here? It means if velocity changes, there has to be proportionate change in wavelength. So any change in V will have proportionate change in lambda. So what does it mean? If velocity becomes double, frequency is why velocity becomes double? Because wavelength has become double. It's just like this. You are running, you take 10 steps in a second. If you take 10 steps in a second, if you take each step of 0.5 meter, you will run at a speed of 5 meter per second. But rather than having taking a step of 0.5 meter per second, if you take a step of 1 meter, but number of steps per second same, your speed will become 10 meter per second. So something like this. So it is like this is size of the step what you run with. So when any change will have proportional change in weight. So what is happening here, as I notice here, at this point tension is different and this point tension is different. That's how we could start thinking. Tension at bottom and tension at top are different. If tension is different, wave velocity here and here velocity is different. If wave velocity is different, here wavelength also is different. So can you calculate what is the tension at the bottom and what is the tension at the top? Then only similar ratio will prevail in whatever ratio I can use this equation. So basically what when we see velocity at the bottom divided by wavelength at the bottom, if velocity frequency remains same, it has to be velocity at the top and wavelength at the top. So can you find what is the ratio velocity? But so if other way of writing will be wavelength at the top by wavelength at the bottom is equal to what? Velocity at the top divided by velocity at the bottom. But what is velocity at the top? Velocity is equal to root of velocity is proportional to tension. And mu remains same. It is equal to tension at the top divided by tension at the bottom. Vikram,
Yes, sir.
have you understood so far?
Yes, sir. So far, I'm clear.
Okay. Now, can you tell me what is the ratio of tension? What is tension at the bottom and what is tension at the top? What is tension at the bottom? At this point, what is the tension in the string? You know how to calculate, Vikram?
Yes, sir. Just a minute.
Tell me. So all of you, what is the tension at the bottom? What is tension at the top? So for calculation of tension at the bottom, for calculation of tension bottom, take this as my system. This 2 kg mass as a system. If I take 2 kg mass as a system, what is happening? Contact force or tension force is acting. It will become like this. Tension at the bottom, mass here, and its weight is acting downward. So what is tension at any point? Tension at any point is equal to weight of the mass below that point of suspension. What is the weight here? Weight is equal to 2 into G. So tension at the bottom, TB is equal to 2G, mass below that point of 2. And what is the tension here? When we take tension here, this tension force supports entire weight. So what is the tension at the top? Tension, this 6 kg mass of the rope plus mass suspended 8 kg. So tension at the top will be equal to 8 kg into 8 into mass is 8 and into g. So tension at the top is 4 times tension at the bottom. So this ratio is equal to 2. If the ratio is 2, with the wavelength at the top will be twice the wavelength at the bottom. Pranav,
Yes, sir.
is this clear?
Yes, sir.
Tensions also you understood?
Yes, sir. Understood.
Okay. So Pranav, if you understood this one, can you tell me what would happen to tension if whole thing is given an acceleration of say 2g upwards? Will the tension here and here remain same or will the tension change? In this question, this case, it was freely suspended. What happens if it is like a kind of lift cabin and if you give an upward acceleration of 2g? In that case, what would be the acceleration? What would be the tension at the bottom and the top?
Like the upward one will increase, the downward one will decrease.
No idea at all. Okay, so you don't understand what will happen when the how would you calculate? Okay, anybody, Halad, what is the tension at the bottom and tension at the top if he is given acceleration of 2g here?
Sir,
What will be the tension at the bottom and what will be the tension at the top if entire system is given an upward acceleration of 2g?
it will be 3 times 8.
Yeah, basically what will happen, we'll replace
4G.
g with effective g. What is effective g? Effective g is g plus a naught. So if it is 2g, it will become equivalent to 3g. So, but still the ratio of wavelength will remain same. So this will become, we'll write not 2 into g, we'll write 2 into 3g and 8 into 3g. I hope, Pranav, have you following?
Yes, sir.
Effective g. So we have seen in case of upward acceleration, effective g becomes equal to g plus a naught, and hence the weight becomes, apparent weight becomes more. Next question. So let's first understand what the question is. Again, similar question. The string is length is L. Okay. And time required for transverse pulse to travel from bottom to half length. Okay. So if total length is L, so if I create a pulse and somebody has created I was reading in Sengage book, they have mentioned very nice question. Just look at this question. There's something, the question was given is something, there's a helicopter. Okay, and you are stuck somewhere, helicopter has come for rescue. Helicopter is suspended a rope from here from the top. And where are you? You can think of a pilot, but you are not the pilot. Where are you? You are hanging by the rope. You are being rescued. You are hanging by the rope here. And because of sound, you are not able to communicate. So, sometimes you can create a jerk here. You can give a kind of tug to the rope. And if you create a pulse at the bottom, the pulse will reach the top also. The question was, if the person was hanging, can we calculate how much time the pulse will take to reach the top? And this kind of questions become important in matter of life and death in some cases. Okay, and this also something similar. So you notice this kind of question, it can be, this same question can be framed something like this. It gives you a real life implication. Real life implication where life is at risk. Okay, so let's see that one. Let's see what is the time taken for pulse to travel. So first thing what we understand here, if it is a taut string, if I create any oscillation here, this oscillation, if you give one jerk here, the oscillation will travel up. It will keep traveling certain speed. So how do we calculate? And let's say this is the point where it is L by 2. How much time it will take to reach from here to here? See, time taken, how do we calculate time taken? Whenever we have to calculate time is equal to distance by speed. Okay, that's how we calculate. Only problem is when the words travel here, what is speed we have to take? We have to take the speed of the wave. But what is the speed of the wave? The speed of the wave is equal to v is equal to root of t by mu. But like previous case, speed of wave here is not a constant. Why speed of wave is not constant? At different points, tension is changing, hence the speed is changing. So this question is calculation of this time where speed is not constant. So what we need to do, again, we need to divide this into small bits here. And when we take speed is varying with x, when we take a small element of length dx at a position x, then speed can be treated for that small element. For a small change in x, speed can be taken as constant. So this question also requires integration. I hope you're following what is the logic behind integration. So every such question, first thing, what thought should have come to your mind? Time required. So how do we calculate time? Time is equal to distance by speed. But speed is varying with x. So what we need to do? We need to calculate, we have to consider a small element. So consider rope to be composed of several small elements. And we take one random element. That's why again called differential element. So let's take a differential element and let's define the lower point at x is equal to 0. This position is x and this element length is dx. So what we'll calculate here, how much time it will travel, how much time does it take to travel from x to x plus dx, or how much time does it take to travel length dx. And similarly, I can calculate time for, I can add it up through integration, I can find the total time. The scheme is calculate, you can several elements and then calculate dt. dt is the time to travel distance dx. And then we can integrate. I hope this idea is clear. Preetham, have you understood how we are going to calculate? Anvita,
Yes,
are you following?
yes, sir.
Can you write an expression? Do you
I
think you
think
can
so.
form an equation?
Yeah,
Bhageshri, can you form an equation now?
Yes, sir.
Okay, so all of you try and form an equation. So this is the approach, and we have already done a tension question. So you should know how to calculate tension. I'll just erase it off, and all of you should write it now. What we have done, we have taken the origin to be at lower end, x is equal to 0, which I have already shown in the figure. As x increases, tension and hence the velocity will increase as well. Thus, we consider a small element of length dx stretching from x to x plus ds, a random element. Time taken to traverse this small element length of dx will be, time taken will be equal to length of the element dx divided by vx. What does vx indicate? Vx indicate velocity at a point at a distance x from the velocity at position x. All we need to do, we have to calculate vx. How do we calculate vx now? What is vx here? This is vx, this is point is x, this is x plus dx. So what is the velocity here? At what velocity it is traveling? That's vx. To calculate vx here will depend on the tension at this point. What would vx be? Vx will be equal to, now let's calculate velocity vx. Velocity will be equal to tension at this point here, tx divided by mu. What is tension at this point x here? Tension at this point will be equal to, tx is equal to mass of this part from free body diagram. Basically from this system, you take up this part as a system, it has weight acting downwards and tension force has to be equal and opposite to weight, then it is in the state of equilibrium. What is tx will be equal to? I assume mu, I am assuming the mass per unit length to be mu. So if mass per unit, mass of this whole piece will be equal to mu into x into g. That's a tx. So mu gets cancelled. The velocity as a function of x will be equal to root xg. Once I have velocity, I can calculate time. So total time taken from x is equal to 0 to L by 2 will be equal to 0 to L by 2 integrate dx divided by root of xg. And if this is up to length, half the length, if it was full length, I would integrate from 0 to L. Hemant? Hemant?
Yes, sir.
Have you understood?
Yes, sir.
Completely or partially?
trying to follow.
Still not clear?
I got it mostly.
Hmm? I hope all are clear. Anybody has any issue with this? All right. A similar question. Okay, then I'll almost time now. I'll stop here. We'll continue with some more question on the same topic in the afternoon session.